Hi, this is my final project on the MNIST dataset with some machine learning algorithms. And I'm going to talk about the dataset a little bit, and then here's some models I've been used for this dataset. MNIST dataset, it is a database of handwritten digits. All the digits have been size normalized and centered in a fixed size. And then there comes with black and white images of size 28 times 28 pixels. And either the pixel is white, blank with a 0, or there's some pixels value. And here's the data set I get from the Kara library. Use the MNIST load data to get the training set and the test sets. There's going to be 60,000 data for the training, and then 10,000 data for the testing. And here's one example I picked for, and then if you choose either one image and reshape it as 28 times 28, we can see the pixels value. You see there's 0 or some number, and this specific sample comes out with the number 4. And then here's some other examples, number 5, 0, 4, 1, and 9. And basically this is the data set. And the first model I use is the logistic regression. I use the basic one, and then it cost me 78 seconds to train the data. And then the accuracy only comes up to 92%. And here's the confusion matrix. You can see there are some numbers are misclassified. The actual label is 5, and the machine will classify it as a 6 or an 8. And then like number 8, the misclassified case then will be number 2, number 3, and number 5. Here's the next model I use, the random forest. Random forest is simply a collection of decision trees whose results are aggregated into one final result. It limits the overfitting as well as the error due to the bias of a normal decision trees you have. And then I have 1,000 trees. That's the optimal that I came out. I tried 5,000 as well, but the accuracy went down. And then total training cost is 7 minutes. And here's the confusion matrix. We can see the text accuracy goes up to 97.2%. And then there's still some numbers that are not as good as we want. We can see number 9 it will be classified as number 7, number 4, and then for number 8 it will be classified as number 5, number 3, and 2. And then here's the next model I use. It's called a support vector machine, which we talked about in the class. And then I use the 0.1 gamma and the polynomial kernel. I've tried the RBF and the linear as well, but it takes longer time, and the accuracy went down a lot. So this polynomial kernel is the best I came up with. And then the total accuracy goes up to almost 98%, and the total training cost is 5.5 minutes. And here's the confusion matrix CXL. And then you can see there's still some numbers will be misclassified, but the error rate is much lower than before. And then the next one I use is multi-layer perceptron. It is a subset of a deep neural network. And then this multi-layer perceptron uses a gradient of the network's parameter to the network's error to adjust the parameters to better values in each training iteration. So it's like this, and the input of the image, which are the matrix, the numpy array of pixels, and then it would just go into different hidden layers, and then the outputs to classify the result. I use the 2 hidden layers. The first one will be 1024, and then the second one will be 512. I've tried other numbers of hidden layers as well, but this one came out the best. And then the test accuracy goes up to 98.13%, and then total training cost is 3.5 minutes, which is pretty feasible, I would say. And then here's the confusion matrix. And then one of the problem for multi-layer perception is that you have to multiply each layer's parameters and the gradients together across all the layers. With 2 or more layers, there's a lot of multiplication, especially if most of the parameters are less than 1 or greater than 0 or greater than 1. Eventually, the gradient just vanishes into machine 0, or the gradient explodes into a huge number. Both situations would cause the training stops. So that leads me to the deep neural network. The purpose is a new initialization strategy. Use a series of single layers networks, which do not suffer from vanishing and exploding the gradients, to find the initial parameters for deep multi-layer perception. Here's are the 2 hidden layers I use. The total training cost for 10,000 steps will be 7.5 minutes, and then the test accuracy is almost get to 98%. And then if the steps get higher, I use 100K steps, and then the training cost will take an hour, 14 minutes, but the test accuracy is a little bit higher than the multi-layer perceptron. And then the last model I use is called the 2D convolutional neural network with 2 filters. This is from the Keras package. The batch size I use is 128, which I think is the default, and then the 10 epochs, that is the how many times of the iteration of the training. And then I use the rectified linear units and softmax method for that. And then the training costs 42 minutes, but the accuracy go actually up to 99.2%. And here's the basic concept of the 2D convolutional neural network. And here's the training. The API shows the training process, each outputs, and then the loss actually going down, which is what we want, and then the accuracy is going up. And then finally, the accuracy goes up to 99.2%. And here's the confusion matrix. Here you can see most of the errors actually came to 0, which is pretty good. For this accuracy, which means for 100 numbers we predict, there's going to be less than 1 numbers we were predicting wrong. So here's my presentation. Thank you.